In this video, I will talk about the Newton's law of gravitation. Every object in the universe attracts every other object in the universe. There is always a force of attraction acting between any two objects. So there's a force of attraction between you and me, although we are very far apart. There's a force of attraction between me and my iPad. There's a force of attraction between me and the wall. So we are always being attracted towards any other object in the universe. And the magnitude of the force of attraction between the two objects is given by the Newton's law of gravitation. And what does it say is this: the force of gravitation is directly proportional to the product of masses. The heavier the mass, the more the force of attraction will be. And it is inversely proportional to the square of the distances. That is, the further the masses are, the smaller will be the force of attraction. And there is a constant G, and this G is called a universal gravitational constant. And the reason we call this as a universal gravitational constant because this value does not depend upon where you are. This value is same at any point in the universe, whether you go to the moon, Jupiter, or anywhere in the universe. This value is always constant. That's the reason we call this as a universal gravitational constant. And the value of G is 6.674 times 10 to the 11 cubic meter per kilogram per second square. The other unit of this one is Newton meter square per kilogram square. Let me write down here. The other unit of G is Newton meter square per kilogram square. That is the another unit of universal gravitational constant. And the SI unit of mass we always measure in kilogram, and the radius is in meter, and the force will be in Newton. Remember, the force between the two objects, or the gravitational force between the two objects, is always attractive in nature. Always attractive. And never repulsive. It is always attractive. That means if you have the two objects here, then the force acting onto this object by this object will be towards this one, and the force onto this object by this object will be towards this way. And the distance between the two objects is always measured from their center of masses. So in this case it is a sphere, a homogeneous sphere, and then the distance are measured from the center. So in this picture, if you look at the two masses here, what does this masses tell you? F21, that is the force acting onto object 1 by object 2, and this one is towards the second object. And the force acting onto this object by this object will be F12, which means the force acting onto object first by object 2. And the direction of the force is the line joining the two masses. So if I have the two masses here, and the force will be always along the line joining, it cannot be in any other direction. It's always join the center of masses of the two objects, and the force will be along the direction of the line joining the center of masses of the two objects. So by Newton's third law of motion, the force acting onto this object by this object will be exactly equal and opposite to the force acting onto this object by this object. That means this value here, F12 must be equal to negative of F21. And remember, these two forces are not onto the same object. These two are on different objects. This force is the force acting onto object 2 by the object 1, and this force is the force acting onto object 1 by object 2. Okay, so both gives you the same magnitude, but the directions are opposite. So for example, there's a force of attraction between you and the moon. The amount of force with which the moon attracts you is exactly the same force by which you attract the moon. It's always equal and opposite. So let me give you some examples of the Newton's law of gravitation, just numerical problems. So here we're going to calculate the force of attraction between two wrestlers. So we have the two wrestlers here. Let's say the masses are 400 kilogram and the other has 420 kilogram, and the distance between them is 50 centimeter, which is half meter. So if by Newton's second law of motion, the force of attraction between them is given by this equation here, G m1 m2 divided by r square. So if I plug in all the values, what I get is this force here, 4.48 times 10 to the negative 5 Newton. Look at the magnitude of the force. This is negative 5, which is very, very tiny, very small amount of force. And there will be, so this is the force between these two objects. So this is a very tiny force, and we won't feel any forces. And the other reason we do not feel the gravitation force is because we are constantly being pulled in all direction. So let's say you are here, then you're being pulled in all possible direction. So the net force by the surrounding objects is always equal to 0. But there is a force onto you by the moon in one direction. So this force is very, very tiny force. And the gravitational force in general, or the gravitational force in fact, is the long range force, that it can act to a longer distance, and this force becomes significant when we calculate the force of gravitation between two heavier bodies. For example, between the sun and the earth, the sun and the moon, the sun and the Jupiter. Let's see one example here. So here I'm going to calculate the force of attraction between the sun and the earth. The mass of the sun is given here, the mass of the earth is given here, the distance between earth and sun, this is the distance between earth and sun. And the sun, and this is the universal gravitational constant. So if you use the Newton's second law of motion, the Newton's law of gravitation, then the force of attraction between the earth and the sun will be this value here. And look at this number here. This is a huge force, 10 to the 22 Newton. That's a huge force. This is close to the weight of the earth itself. So this is a significant amount of force here, a huge force. And this force, the gravitational force, the gravitational pull by the sun on the earth, or this force keeps the earth in its orbit. So if there was no force of gravitation between the sun and the earth would not be moving in its orbit around the sun. It would fly away. or for some reason, if sun disappears, then there will be no force of gravitational attraction between the sun and the earth, and the earth will fly away, or it will start moving in a one direction or in a linear motion. It is the force of attraction by the sun on the earth which keeps the orbit to move around the sun, okay, or it provides the necessary centripetal force for the earth to be in its orbit around the sun. Okay, so this is it from this video. If you have any questions, write to me. Thank you very much.